We're going to continue this session on cosmic flows. And the first speaker is going to be Nicolas Bouche. He's going to tell us about constraints on gas and metal flows. Right.
Thank you very much. I would like to thank Joel and Avishai for giving me the chance to come back here on the coast of the Pacific Ocean, which is a very, very nice place to be. I am now at this University of Toulouse, which is also in the southern part of France, where you have good weather, but no ocean. We are as far as you can get from the two seas. But of course, one of the main reasons why it's interesting and I wanted to go and be there is to be part of the MUSE collaboration. So you'll see a lot more of the MUSE results. Today, what I would like to talk about is the constraints on gas and metal flows from background quasars, as the background image might let you see what the subject might is. So this is from the ESO press release image of the three canonical flows feeding a galaxy with the background sources here sort of illuminating or giving light to the presence of the cold flow disks. And before I go on more on the details, I would like to point out that most of the work has been done by my student, Ilan Schroeder, Eli Finlay, a postdoc also with us, and some of my excellent collaborators are listed here. Okay, so I think this is kind of the emerging picture. I think we had a lot of nice introductions by Kyle and also Colin about this scenario when you have these streams of cold gas feeding the central objects, forming a kind of coplanar structure. Some people now refer to that as cold flow disks. And then you have these biconical outflows perpendicular to the disk. And this is a new picture, an emerging picture that's coming out in the past few years, not just from these simulations that we heard about in the past a few days, but also from observations. And I would like to convince you that observationally, there is very strong evidence for this scenario. So you should visualize this in the central region here with this cold flow disk from Kyle. And of course, there might be also some recycling of this outflow material can come back, as Colleen explained this morning. The questions we want to address is like, is the outflow material enriched? Is the inflowing material metal poor? And also, we'd like to know more quantitatively what's happening in the mass fluxes. How much mass flux are in each of these components? How far does the wind go? And is there an acceleration profile that you could detect in the observations? For the inflows, we'd like to know how much gas gets in, or whether it comes in spherically symmetric or like in this picture, and how much gas. These are very critical, very important questions we'd like to address from the observations. I could give a 20-minute talk on each of these aspects. I just want to highlight the results that were published in the past few years, and some which is going to be an Astro PhD in the next few weeks on this recycling, where we have constraints both on inflows and outflows on a single galaxy. Before showing you the results, just one slide to motivate the problems. The well-known challenge in galaxy formation is that we have a tension between simulations and observations, particularly these low baryon fractions, or the star mass in this case, as a function for number density of galaxies, a function of stellar mass. In this illustrious simulation, clearly shows an excess compared to the observed faint slope. And probably the reason why they couldn't match these observations is because they would have destroyed their disk, the very nice, beautiful disks where you have a nice morphology reproducing the observations. So you have the tension here between cranking up the amount of feedback you have and trying to match the baryon content of galaxies. And also, if you look at all of the simulations, including the fire simulations, the loading factor, or the outflow rate to the star formation rate as a function of halo mass, you see there's a large range of values or for the subgrid physics or for the measurements that you have in the simulations. There's clearly no consensus. There's an order of magnitude here in these different simulations differences. So what you would like to do here is to put observations on this diagram. And traditionally is to use galaxy spectroscopy. So you take a galaxy spectra, and in these observations you only see kind of a blue shifted absorption line from low ionization lines like sodium or magnesium. But there, as was mentioned already this morning, you don't know where the gas is. It could be 100 parsec in front of the galaxy, kiloparsec, or 10 kiloparsec in front of the galaxy. You have no idea. So the only thing you see in these observations is the outflow speed. And you need a lot more information to get the outflow mass flux. You need the location of the gas, the column density of the gas, and also the opening angle of the wind, whether it's spherically symmetric or more biconical flow. I think some of the state-of-the-art also is using emission measurements, and there you have tighter constraints on the location of the gas to constrain the outflow fact from these emission signatures. I think with the new generation of IFUs, pretty soon we'll be able to spatially resolve these emissions in single galaxies. But today I would like to stress that background quasars passing near star-forming galaxies are very powerful tools to constrain the outflow rates, because we have the location of the gas from just the impact parameter to the galaxy. We can constrain the outflow speed also by reconstructing, deprojecting the outflow speed. And we have measurement, either direct or indirect, on the column density from the background absorption line. And statistically, we can constrain also the opening angle of the wind. So we have all of this information to constrain that to put very tight constraints on the outflow rate. The main advantage also on background quasars is I can probe winds around or gas flows around any galaxy. Two of the problems are listed here, that they are rare, so you have to devise strategy to build large samples of galaxy quasar pairs. And also the other problem is that you can probe anything else, not just outflows, but maybe also accretion. Depending on the orientation of the galaxy here, you might have a very different physical interpretation. Like in this case, you might interpret the signature you see here in the background quasar as probing the extended part of the disk, whereas in this scenario, where the galaxy minor axis is more or less directed towards the quasar sightline, you might be interpreting this in an outflow. So it's critical to have this relative geometry constraint very precise from the observations. And because this is so important, I want to advertise here one of the tools that we are using now to constrain this is this 3D fitting tool, UC-HiPACC, where we take the data cube, which is represented here, and to fit a galaxy model directly to the data. Taking into account the PSF and the line request function, we can then constrain the morphological parameters and the kinematic parameters directly and return the sort of the intrinsic or deconvolved properties of the galaxy. And this is very, very important, and it was challenging and technically difficult, but we have been able to do this. In the case of low signal to noise, and also in the case of course, when the signal to noise is higher, when we get tighter constraint. And to illustrate this, here on one example, where we overlay the data, in this case from Symphony, with a model. In this case, you have the z-axis is the velocity axis. You have a little sort of asymmetric, maybe minor merger, or that is not really affecting the fit here. But on the right, you see here so the proof of the concept, where we have the inclination from this ground-based observations with μ's, and on the x-axis, you have the sort of HST morphologies in the DFS south. So you see very tight correlation here with a small, maybe systematic offsets, but this shows that we can constrain from ground-based observations the inclination of the galaxy from IFU data. And that's very important for untangling the information in gas flows using background quasars. We have been using different strategies over the year to build large samples of galaxy quasar pairs, a galaxy-selected sample, where we start with Sloan galaxies around shift 0.1 to 0.3, and then look for quasars that are around 150 kiloparsec, and then do follow-up with LRS, for instance, to go after the low ionization lines. Or you can do the alternative, is to start with a sample of magnesium-2 observers in Sloan also, when you have large samples of catalogs, of quasar catalogs, when you can extract large samples of magnesium-2 observers, and then you look with Symphony or with MUSE and IFU for the galaxy responsible for this absorption. And we have been very successful with this technique with 70 or 80% success rate. So far with MUSE, we have 7 fields observed, and 14 will be observed in the second year of the GGO program. So from these galaxy quasar pairs, now we have to select the pairs that are favorable for winds. And we do that by looking at this result, which really shows that the absorption of magnesium-2 observers around galaxies is not distributed spherically symmetric. You see a strong excess at the low angle from the major axis. This is the azimuth angle. And also an excess along the minor axis. And this already back then in 2012 was one of the first evidence that this distribution was non-spherically symmetric. And since then, there's been a lot of work in the literature using background galaxies or larger samples, and they're all sort of confirming this for strong magnesium-2 observers above 1 angstrom or so. So that gives us a statistic constraint on the opening angle of the wind, of which is around 30 degrees plus or minus from the axis symmetric. So now the thing is, from this magnesium 2 selected sample, we have, the magnesium 2 line is highly recognizable in Sloan spectra with low signal to noise or even. And we can now just use an IFU to find the galaxy at the redshift of the absorber. So we just have to tune the IFU in the wavelengths that we expect for star formation signature like H alpha or 2, and we can see the galaxy popping up. And so if you didn't believe the previous histogram, this is now the newest result from the mu sample. We see this bimodal distribution again. So combining the two samples, now we have a sample about 20 galaxies where this bimodal distribution is very strongly present. So it really shows that there are also strong large amount of gas in the other parts of galaxies, both on the major axis and the minor axis. In fact, if you look at the equivalent width impact parameter distribution, you find that they have different relationship between distance, between impact parameter for these two cases. This is steeper than that one. If you want, I can discuss that more later. So now we have this geometry. We have our galaxies and quasar pairs. What we want to do is to compare the kinematic we see in the quasar sightline to a sort of a very simple wind model with one free parameter. So we assume just a mass-conserved flow. So the density of the clouds in the wind goes at 1 over r squared. And the free parameter is the outflow speed, which we assume constant because we have an impact parameter which is, for instance, here. So any variation of the wind speed with distance would not be seen in our data. And we can then, using the geometry from observations, shoot sight lines through this biconical flow with respect to the observation and compare that to the kinematics in the quasar. So here's one example from the Symphony plus UVS program, when you see here the Symphony flux map and velocity map, where we have also a good constraint on the inclination, of course, which we verified in HST archival images. And now, because all of the geometry is fixed for the biconical flow, we can ask the question, are the kinematics in this sight line that you would get from this very naive, very simple wind model consistent with the observations? And here you see that the model is shown here and the observations is here, and they are very consistent. In fact, extremely consistent. We can account for this asymmetric shape by just the inclination of the galaxy with respect to the sight line. If the wind were perpendicular to the sight line, this absorption line would be very symmetric. So now we have a constraint on the outflow speed, which typically 150 km per second to 200 km per second. And I should say that the outflow speed are always more or less smaller than the escape velocity at that distance. We have a constraint on the gas location. We also have, some cases, direct constraints on the amount of gas with cost observations for the total amount of gas. And statistically, we have a constraint on the opening angle of the wind. So we have very tight constraints on the outflow rates from these observations. Here are the results, where from the loading factor as a function of the halo mass, for the few cases where we are able to do it, we find loading factors around unity. We don't have a large dynamical range to address the question whether this depends on mass or not. We don't go in the mass regime of the fire simulations when there's a turnover around here. But soon, maybe in the next few months, we'll be able to do that with larger samples. On the left, you have this distance dependence for the equivalent width as a function of impact parameter, and you see there's a very tight scatter here that follow the 1 over b expectation for sort of a mass-conserved flux. So this is another evidence that this kind of biconical flow scenario fits the observations very well. So in summary, from the studying of outflows using background quasars, we can address these questions directly. Does the wind escape? It seems like it does not escape. In one case where the impact parameter is below 10 kiloparsec, we have signs of acceleration. If you want, you can ask me for it later. It seems like from this impact parameter distribution I've shown you before, they travel up to 100 kiloparsec, and then we a lot of loose trace of this gas. We don't know if it carries enough mass, and we can't tell yet whether the dependence is 1 over v or 1 over v squared. But stay tuned for that. We'll have more results shortly. So if winds do not carry or do not remove the baryons, then where are the baryons? Well, I think it's good to always remind ourselves that there are two possibilities to solve the low baryon content of galaxies. Either you invoke this ejective feedback, or more this sort of preventive feedback where you prevent the baryon from coming in the first place through changing the ionization from the local ionization sources, for instance. Okay, so that was for the outflows. Now I want to turn to the sight lines that are more or less aligned with the major axis. We hypothesized at the beginning, a couple of years ago, that this was a good probes of the extended part of disks, and now we have a term for this. It's a cold flow disk. As motivated by these observations from Pierre Madaro, when you see these inflowing particles are more or less aligned with the galaxy, this edge on in this case, and also on the right you have the outflowing particles that are perpendicular to the disk. So are the kinematics then in this case consistent with this cold flow disk scenario? Well, we had one case in 2013 where we put direct constraint again, playing the same game on the accretion rate, because we have a constraint on the amount of total gas. There was a DLA in this case, the location of the gas, and also the accretion speed. And the accretion speed constraint comes from the same technique as for the outflows. We compare the kinematic profile that we see in the low ionization lines to a simulated profile, and we find that these low ionization profiles do show the expected signatures for cold flow disk that Kyle talked about, in the sense that there's a lot of gas with smaller velocities compared to the rotation speed, which is about here in this case. And we can then turn it around and constrain the accretion speed. Interestingly enough, the gas is not pristine. In this case, the metallicity was around -1, and then at redshift 2, and then redshift 1 now. This is the next example I want to show you from recent observations with MUSE, where we have a lot of information by combining MUSE, Symphony, and also COS from HST, and of course UVES for the quasar spectra. So MUSE is great, has a very much wider field of view, 1 arc minute. It's not just great because it has a wide field of view, but it's great because it has a huge throughput, higher than any of the spectrograph on the VLTs. You see here the throughput reaches about 45%, including the telescope for this instrument. So here you see the whole field, in this case, with the galaxies labeled with the different redshifts, with the quasar and the cross. And we can do a narrowband extraction at the redshift of the magnesium 2 observers. And we find 2 objects next to the quasar, this one and this one, which is very far away, 300 kiloparsec or so it's not related. We can go very deep, just 1 hour or 2 hours in observations. We have a star formation limit of 0.1 solar masses per year. So this galaxy is really isolated. There's no neighbor down to this limit. And its star formation rate is around 5 solar masses per year. We can extract the kinematics using the technique as I showed you at the beginning. You see here the velocity field, and the location of the quasar is shown there. And I will come back to that point in a minute, but just to highlight some of the quality of the spectra here we have on the right. You see the O2 and the H beta for the galaxy, and then on the black curves and absorption for the magnesium 2, also towards the galaxy, and also the iron 2 absorption towards the galaxy. If you look at this and compare the absorption of the galaxy compared to the quasar absorption of the CGM, you see that the galaxy shows blue-shifted absorption lines, as you would expect for an outflow, and you can constrain the outflow rate, in this case, with large asymptotes of 0.5 to 5 solar masses per year if you push it. Now, there are no direct signs of emission, but some indirect signs of emission. If you want, you can ask me about it later. But now I want to turn to the accretion signatures, looking at the low ionization magnesium line, comparing the kinematic profile with more details. And you can see here the result of the observed profile compared to the simulated profile, where we can account for this higher component at 60 km per second from the rotation speed. But again, we see a large number of components with velocities less than the rotation speed, pretty much as expected from the simulations by Kyle and others. So now we can play, as in the previous case, play the same game to constrain the inflow rate, and we have an inflow rate in this case of 5 to 15 solar masses per year. That is 2 to 3 times the star formation rate, and an outflow rate about 0.5 to 5 if you push it solar masses per year. In this case, the metallicity also, we have a constraint on the metallicity from the metal lines. And the metallicity is quite large. It's not pristine at all. It's around half sorum. So that's already a good sign of recycling, because this is not a gas coming in for the first time. So now we have two cases where we can constrain directly the sort of accretion efficiency. So the ratio between the star formation rate to the accretion rate. Two redshifts, redshift 1 and redshift 2. Interestingly enough, the redshift 2 case lies in this regime where Avishai would claim there's also a hot halo, which we have signatures for in carbon 4 and oxygen 6. And as we push more towards the low mass regime, we maybe put constraint on this accretion efficiency in the low mass regime in the next few months or few years. So for my conclusions here, going back to the questions I asked at the beginning, do the winds escape the potential of these halos? It seems like the answer is not, because the wind speed are too small, they're too low compared to the escape velocity. How far do they go? They go up to maybe 100 kiloparsec or so. The mass loading is still relatively low if you wanted to account for the low baryon fractions of 20% or so in L-star galaxies. And for the inflows, we have signs and evidence for this cold flow disk through background quasar signatures that are more or less aligned with the major axis, with an inflow rate comparable to the star formation rate. And that's very interesting, and if you ask the question, why is the inflow rate comparable to the star formation rate, then we all know the story with the vast depth scenario, where this star formation rate is regulated by the amount of accretion that comes in. And so I have to put my favorite movie, SPH movie with gravity here, showing that the cold flow of cold streams diverted from a simulation reaches a steady state where the star formation rate is proportional to the accretion rate. So I'll take your questions. Thank you.
All right. Are there questions? No? No questions? No.
Excuse me. So you mentioned this acceleration within 5 kpc, but I don't think you show what's happening there.
So in that case, yeah, we do have some evidence that the gas is being accelerated in the first 5 kiloparsec. And it comes from the fact that the absorption profile has a symmetry that is opposite from what you would expect if the profile would be, if you were in the region of the flat profile. So in the region of the flat profile, you have these inclination effects that create an asymmetry in the profile that is opposite from what you see. So the asymmetry is on the other side of the systemic. In this case, we have symmetry towards systemic, and we can account this from an acceleration profile. This is also the case when the impact parameter is the smallest. I forgot exactly what the number, but it's 5 or 6 kiloparsec.
Any other question? Well, if not, let's thank Nicolas again. And so the next talk in the